Hello. Hello, everyone. We want to start in 2 minutes, so please take some seats. Should we start? All right. Yeah. Hello. Welcome, everyone. My name is Timur. Welcome to the very first ever London Audio Programmer Meetup. This is super exciting. I can't believe it. It's like the first time we're doing this. So me and Josh over here. Where's Josh? All right. Yeah. So we are your hosts. This is the first edition, and we're doing this the first time, and we're already booked out. We have a full house. This is absolutely amazing. Thank you so much for coming. This is super exciting. I'd like also to thank our sponsors, Focusrite and Sonics. So please, round of applause for our sponsors. Yay! I think some people from Focusrite are actually here tonight, right? Yep. Hello. Welcome. I would also like to thank Strongroom, which is this venue, this amazing venue here, for having us here. And please support them by buying drinks at the bar. They're amazing, this is great. What else? So obviously, we want this place to be kind of inclusive and safe and diverse. So what we would like to do is we'd like to ask you, so this is like a place where no matter what your background is, no matter where you are in your journey, becoming or being an audio developer, this should be a good place for you to be. So please be nice to each other, be polite to each other, be respectful. We have a code of conduct, which is the, sorry for that. Which is the Berlin Code of Conduct, which you can find at berlincodeofconduct.org. So this is going to happen every second Tuesday of the month, starting tonight. And the next one is going to be the next second Tuesday of the month, which is going to be Tuesday the 14th of April. Here at the same time, we're going to announce a speaker soon. Speaking of speakers, if you would like to speak at this meetup, please let us know. Please write an email to Josh at josh@theaudioprogrammer.com or to myself, mail@timur.audio. And yeah, we welcome experienced speakers, first-time speakers, anything in between. You can do like a really short one, you can do a longer one, you can talk about anything you want as long as it's related to audio programming. Please let us know. It's, I think it's a nice place to give a talk, and we want to have a good range of different talks. So it would be amazing if many of you would be presenters here. So yeah, let us know about that. Tonight we have the following agenda. So I'm going to start talking a little bit about C++ 20, and then we're going to have our main speaker for tonight, Dave Rowland over here, talking about real-time trade-offs. And then to conclude the evening, Josh is going to talk to us about an introduction to Juice. All right, so let's get started. So obviously, okay, let's ask a question first. So who here is an audio programmer? All right, most people. Who writes in C++? All right, quite a few people. So obviously C++ is by far not the only programming language that can be used for audio and music stuff. So obviously this is not a C++ meetup. This is not going to be C++ meetup. We're going to have a wide range of topics with other programming languages. So if you're not a C++ programmer, I hope we're not going to scare you off. Well, I'm not going to scare you off now. It just so happens that C++ is kind of my area, so I'm going to talk about that tonight. But you know, it's not about C++. We're going to have other programming languages as well. Speaking of which, let's talk about a little bit about C++. So before we do that, let's talk about this place. Anyone knows where that is? This is Prague. All right. So what does Prague have to do with C++? Does anyone know that? All right. So if you might know that C++ is made by a bunch of people who are the C++ committee. And there's a new standard, basically a new specification of the C++ language coming out every 3 years. And the committee, of which I'm a member, meets 3 times a year, which means every new release is 9 meetings. So these are the last 9 meetings of the kind of C++ 20 release cycle. And as you can see here, the last one, the 9th and last meeting of the current release cycle happened in Prague. And that was just 3 weeks ago. And what happened in Prague is that we finished the new C++ 20 standard, which is now done. So C++ 20 is now technically finalized. So I think that's cool. It's not officially published yet because there's some ISO bureaucratic stuff that's going to take a few months, but like I think a month or 2 from now, it's actually going to be like officially the new international standard for the C++ programming language. But like all the technical work is done, the ink is dry. There's a nice YouTube video here, which you can, if you Google C++ 20 is here, that's going to be like the first result with a few things, what actually happens at a committee meeting if you're not working on the specifications. So it's a bit funny, you can check that out. One of the things that happened there at this meeting a few weeks ago is that we had a kind of party to celebrate the release. Of course, if you make a release, you always have a release party. So that release party was pretty epic. We were in like this big Gothic church, and it was really special. We made this picture in the end with all the people who were there, and quite a lot of people. So that was really cool. And I just want to talk a little bit about what's in this new release, what's in the new C++ 20 version. So there's, I think, about 100 features there. But I think these 6 are kind of the most important ones. So we have coroutines, we have concepts, we have ranges, we have modules. You can now use floating point types like float and double, and also user-defined kind of classes as non-type template parameters, which is really cool for audio if you want to write, for example, lookup tables and template them on some kind of floating point parameter and things like that. That's really, really cool. And you can do a lot more stuff at compile time because there's a lot of things that are now const expr, like std vector and std string, which you now can use at compile time, which is pretty cool. So, and I think out of these like 100 features or so that we have there, these 6 are the most important ones because they don't just give you like new tools or new ways of writing things, but they'll actually change the way you think about code. Oops. That was not good. This does not look particularly safe. I'm gonna stand a little bit over here. Yeah, we're back. Okay, sorry for that. Right. So these 6 features, they're gonna change the way we think about functions, classes, the way we design libraries, the way we compile our code or like arrange our projects. So they really will. Hello? All right. Cool. So let me just talk a few minutes about some of these things. Let's talk about coroutines. I think this is probably one which is particularly interesting for audio if you're doing audio in C++. So coroutine really is kind of a special case of function. So what's a function? This is kind of our mental model of a function. It didn't really change since the 50s. So basically the idea is you call it, you might pass it some parameters, which is not actually important here. It's going to run some code, and it's going to return some value, right? This is the concept of a function, which didn't really change the last 60 years. Now, if you want to call a function, let's say you want to call a function that returns something different every time. Let's say we want to have a function f, and we want it to return 0, 1, 2, 3, 4, 5. How would you do that, right? So in order to do something like that, if you don't want to like pre-allocate the whole thing in memory up front, you need to have some kind of external state, right? So you can't really do it with a function. Maybe you can have a counter, which is like a static object, or you can write a class. You can write, and then the class has members, and then you're thinking about objects and classes, and everything becomes a lot very complicated. And I don't think for something like this is really the right way of think about this. With coroutines, we can actually do it much easier because a function already has a state, right? It has local variables inside. So with the coroutine, what you can do is basically, it kind of extends this mental model of a function. So you can have a function, you call it, it runs some code, it maybe initializes some local variables, and then that's the state of the function at this point in time. And then it can yield a temporary value and suspend. And next time you call it, it's going to just continue and yield the next value. But it's going to kind of remember all its local variables. So you don't have to create a class, anything like that. So what you can do with coroutines is you can, for example, say, all right, let's going to have a counter I, which is just a local variable, and just have an infinite loop, and every time around the loop, you're going to increment it and yield the value. And then every time you call it, it's going to yield the next value. So that's like really kind of simple, efficient, kind of low overhead kind of way of doing this. It gets even more interesting because we don't just have yield, we also have a weight. And what a weight actually does is, so if you say you have a function f and you say co-weight g, what actually happens is it returns, but also it resumes if g yields a value, right? So it's kind of this cooperative thing where a function returns, but if this other function g then yields a value, then it's going to jump back into f. So what actually happens here is that if you say co-weight g, you're kind of registering a callback for when g is going to be called, and then you return. And then if g is being called on a different thread, and then yields a value, then you're going to call back into this thing. You're going to resume f again. So, and that can happen on a different thread, right? So you kind of register a callback, return, then on a different thread, someone call g, and then g yields a value, and then basically the second half of the function on the left is going to turn into a callback for g. But the cool thing about this is that you don't have to write any of the stuff yourself. The compiler is just doing it for you. And it's doing it very, very efficiently. So, you know, in audio, if you write this in C++ or similar programming languages, you sometimes end up in this callback hell. You do a lot of stuff with callbacks. You don't have to worry about this anymore, ever. If you do this with coroutines, I actually tried this, and this is true. Like, the code becomes half as long and a lot easier to reason about. So I think this is really going to change the way you write audio code if coroutines become accepted by the community. I'm really looking forward to audio code being written in coroutines, and maybe someone can give a talk here about this at some point. The other thing is concepts. So let's say this is something that actually happens in my day job quite a lot. Let's say we have a function that checks whether an integer is a power of 2, right? This is a very useful function for audio. So this basically is a clever implementation here. It returns true if you have exactly 1 bit set. But it only works for ints. Of course, you want to work it for any integer type. So in C++, you make it a template. OK, great. Now you call it with something that is not an integer type, right? You want to call it with maybe a double, and then that doesn't work. But then the error message you get is it doesn't really tell you what that means. So if you try to call it with a double, it's going to instantiate the template. But then it's going to fail because some of the expression inside doesn't quite, so the compiler is going to hit an expression that doesn't compile for a floating point number. And you get this weird message where you have to look into the implementation to figure out what's going wrong. This is kind of the problem with templates. So, okay, great. You know, we can say static assert that it's an integral type. That's cool. It's going to give us a much better error message. But what if you want to implement this for a double or for a float, right? Whether a float is a power of 2, and we want 0.5 to be a power of 2 as well. There's actually a clever implementation for this, where you kind of can use the std_frexp to kind of decompose a floating point number into mantissa and exponent. Doesn't really matter, it works, but it's very different, right? So this function looks very different from the other one, and this one is for integers, the other one is for floats. And now if you want to call it with a float, what you get is another error, which is saying, well, you redefined the same template 2 times, you can't do that. So now you have to do sphere and enable if, and I'm not sure if anyone has done stuff like this, but you have this horrible template meta function, and where do you stick it? Do you stick it on the return type, but then you don't see what the return type is? Do you stick it in the parameter list? No, you can't really, it doesn't quite work, so you put it in the template parameter list, but then that doesn't work, so you have to make it a non-type template parameter. So this is completely unusable. I can never remember how to do this properly. You shouldn't be doing this. So in C++20, you can just use a concept, right? And that's much better. So you can put it here, and actually it tells the reader much clearer what's going on. And actually there's different ways of writing this. This is like the long form. Oops, sorry. You can write it a lot shorter by just putting it here inside the template parameter list. And you can also, at the top, you can just omit the whole template thing and just make it an argument. And now it's like really short and really nice. But it's not just a way of doing sphere more easily. It's like a whole kind of concept in itself which changes the way you design libraries. So these concepts like integral, they're composable. You can say, well, maybe I have an arithmetic type, and that's if a type either is integral or floating point. And then C++ is this annoying thing where it thinks that character types like char and unsigned char are also arithmetic types. So you're going to say, well, maybe I have a number type, and that's arithmetic, but not if it's a character. And then you have this new number concept. And then you can just write a function like this. And this is a template which is going to take any number. But you don't have to write all this template meta programming boilerplate. It becomes really short and really nice. And then you actually can even say, well, I want to accept types that have a certain interface. So for example, if you want to write a hash map, you want to accept any type that for which you can compute a hash. So you can say, well, if this expression with the hash compiles and returns something which is convertible to size t, basically like an integer type, then this is a hashable type. And you don't have to introduce like a base class like what you would do in Java. You just say, well, if this class has this interface, then it should compile. And you express this in code. Like previously you would have to express this in the documentation maybe, and then the user would have to when they hit these really long unreadable error messages, you would hope that they read the documentation. Sometimes they don't. Now you can express this in code. So I think this is really nice. And then you can say, well, your hash map is going to be a template on any type that has this interface. So the last thing I want to quickly mention is modules, because modules are actually, I think, the most important, by far the most important feature of everything we have in C++20. And modules are the thing that's going to replace headers. And I'm sure everyone who has done C++ is familiar with the pain you have to go through if you program with headers, right? So first of all, you have this weird split between header and source files, but then if you're writing a template, it has to be header only, so it's kind of weird and inconsistent. Then, depending on the order in which you include headers, you might get different results. You might get weird errors, and then you kind of randomly start switching your includes around until it compiles. I'm sure everyone has been there. I certainly have been many times. And then, when you find the error, it turns out, well, this is because you defined a macro before you include, and it kind of leaks into the header, or you have to find the macro inside your header, and then it leaks out and affects the next header that you include. So it's like really messy, and you can have cyclic dependencies between headers, and then, again, it depends kind of on the order. Headers don't really let you encapsulate anything, because everything that's in a header is just going to get copy-pasted into your source file. You don't have any way of saying, yeah, but you're not supposed to use this class. This is like a private thing. There's no such thing for headers. So some people do like a detail namespace or something, but it doesn't really work. And then also, it's very slow to compile, because on the one hand, if you have headers and then you include them and you have translation units, it's nice because you can parallelize it, because every translation unit can be compiled on a different core or whatever, because they're independent. But on the other hand, if you include the same header 100 times, you have to parse and compile a header 100 times, and that's really, really, really slow. So modules basically fix all of this. So just very briefly, if you remember our little power of 2 function, now you can stick it in a math module, and you can say export. And if you don't put the export, then it's private, basically. And this is not a header. This is what we now call a module interface unit, which is like a new thing. It's not a header, not a source file. It's this new thing. And the difference here is that no macros can leak in, no macros can leak out. It can't cyclically depend on anything. And then what the compiler does with it is turns it into a BMI, or it's called a binary module interface. So it's actually going to transform the code into something where you can really quickly, the compiler can really quickly look up all the names in there. So it's going to be really fast to compile. And then you can do something like this, where you can say import math, and this now looks a lot like Python, which is actually really cool. And now if you have multiple imports here, then the order doesn't matter, so you can't have cycles. All of this pain is going away. So you just say import math, and then you can use this function here. And this is really nice. So I don't want to talk too much about this. I have actually, just 2 weeks from now, I'm going to talk for 90 minutes about all of this stuff if you want to know really how all this works. It's going to be at the ACCU conference in Bristol, which is a couple hours on the train from here, and I think it's going to be on YouTube afterwards. So where I'm going to like properly explain what this means, and I think these features are going to really change the way you write audio software in a good way. And actually, the support for this is kind of really, really good already. So there is this long list on CPP reference, like which compiler supports which features, and the first few columns are kind of the important compilers, and unless you do embedded. So there you might have to wait a bit more to get these features, but if you're doing desktop or mobile software, then most of it kind of already works. Like, for example, GCC doesn't do coroutines yet, I think, and so there's a few gaps, but I'm pretty sure that by the end of the year, basically all of the major compilers will support all of these features. So we're going to get to use all of the stuff really, really soon, even if you're doing cross-platform software. Right, so this is kind of everything I wanted to say about C++20 today. I think this is really going to change the way we write code. Right, so I'm done. This was kind of a little introduction talk. Now we're going to move on to the main talk of the evening by yeah? One question? Oh, yeah, do you have questions about this stuff? Sorry.
One quick question.
Yeah.
So Mike asks, how do coroutines in C++20 impact the stood audio proposal? Is the callback approach still the proper abstraction?
Well, that's a good question. Should I repeat the question? Maybe that was not. So the question was, because we're working on the stood audio proposal as well, how does the coroutine stuff, which we now have in the standard, affect that proposal? It's a good question. So obviously we could go ahead and rewrite the whole proposal in terms of coroutines, and actually someone did that, like Frank Birbacher went ahead and kind of made a version of the callback interface using coroutines, and it kind of looks nicer. But we're not sure yet, because if you had a model where you would yield like one sample at the time, it would be like really straightforward. But what you actually do is you do like buffers. So you would have to yield one buffer at the time, and you would kind of. So at the moment, we're not convinced that specifically for the audio proposal, the coroutines are going to lead to something which is a lot better. But this is basically future work. So this year, I think we're going to spend some time looking into this a bit deeper and decide whether we should go for coroutines. I think it's an open question. So thank you very much for the question. I'll keep you updated. I don't actually know the answer yet because we haven't decided yet. We haven't looked into this in enough detail yet. Right. Any other questions about C++20? No. Okay. Well then, thank you very much for your attention. And I'm going to pass over to my very good friend Dave Rowland over here, who is going to deliver his talk. So big applause for Dave. All right. Close this.
Come back. Okay, so my name's Dave Rowland. I'm the Director of Software at Audio Squadron. We have brands like Traction. We make a DAW called Waveform and a whole bunch of plugins and synths. We have Prism Sound, which make high-quality audio interfaces, and the Sadie Digital Audio Workstation as well. A couple of quick notes before I kind of jump into this today. A few questions to start with. Timur did ask, but I couldn't quite see the show of hands. Who here does audio programming? Okay, the majority. Who does real-time audio programming? Oh, that's actually less. Okay. What? Well, we're sort of defined that. Well, we already did. I'll come back to that. Who uses Juice? Okay. Not so many people. there's quite a bit of code today, but try not to get bogged down in the details because it's really the concepts that I'm talking about, but I need some code to back up the examples, to back up those concepts. So, well, it's one spoiler, actually. There isn't a right answer tonight. This is how you do this thing. This is how you think about this whole group of things. So did anyone see me and Fabian give this talk at ADC? A couple of people? Okay. If you haven't seen it, I know I'm sort of self-promoting, but Fabian's part of this as well, and he's really good. Go and watch it, because it gives a really good primer on what real-time really means and some good paradigms to follow. So a bit of background for this talk. When Timor said, do I want to speak about something, I thought, oh yeah, there's this thing that I've kind of been working on that some people might find interesting. And it sort of stemmed because I was slightly bored one day and reading the Juice forum. And Rusty Pine sort of brought up this situation where he said, hey, trigger async update can get called from the real-time audio thread, and is this problematic? And there was a bit of conversation after this, and I sort of said, well, has anyone actually measured this? Have we tested whether it is real-time in practice? So Jim did the hard work. He ended up testing the time it takes to call effectively trigger async update, and he ended up with this number of 47 milliseconds. So does anyone know roughly how long an audio buffer is? 2-ish milliseconds, give or take, depending on your buffer size sample rate. That's a lot smaller than 47 milliseconds. So we have a problem. We kind of need to look into that. So the first thing I did was I went to the MSVC documentation, because this was Windows he was specifically talking about. And I thought, what does post message say? Are there some options you can send to it to say, hey, do this in a real-time safe way? And the answer was no, basically. And there's nothing on here that says it's wait-free, which is essentially the magic phrase that we're looking for. There's also some other caveats in there that say it can fail if the queue is full and things like that. So we kind of need to be aware of those. Although I think, Ed, did you fix that? Yeah, so if you use it in Juice, it's fixed now. I'm going to rewind slightly a little bit, though. Does everyone know what an async updater is? Just kind of abstractly. I had one hand, so not enough. Okay. So the idea of an async updater is that it's essentially a callback that you can trigger lots of times, and at some point in the future you will get one callback. So it's for coalescing lots of notifications into a single action. Does that make sense to everyone? If you do have any questions, just shoot your hands up and I'll ask, because this is basically me rambling for about 30 minutes. Okay, so I thought I'll pick up Jim's train of thought and try and replicate this and figure out how long it takes on a bunch of my machines to call this trigger async update, effectively post a message to the message queue. So this Mac, well, not this one, this one's Timor's, but my Mac did it in worst case around 160 microseconds. This is microseconds on the side here. And these graphs, I'm going to be showing quite a lot. What they show at the bottom is the minimum. You can see on the windows there's a bit of a gap there. The top of the green is the average, and the top of the yellow is the worst case. So we're really interested in the worst case scenario, because that's what's going to cause us buffer overruns. Okay, so I then tested via Windows VM on my machine, and I wasn't able to replicate that 47 milliseconds, but I got around 300 microseconds, which still isn't good. If you think about this being called a lot in a single audio callback, you could very easily go over that 2 milliseconds-ish window. And then I tested on a couple of other machines and got kind of similar 150-ish microseconds, but not great, basically. And also, it's worth noting, this was in a test harness, and all I was doing was hammering this function. In a real-world application where you've got lots of things interacting with the message queue, these numbers are probably going to look a lot worse. So this was a slide that me and Fabian showed at our ADC talk on real-time programming. And we essentially boiled everything we spoke about into one statement, which was don't block. And blocking is essentially anything that is a system call or waiting to acquire a lock of any kind. So if we're trying to make something real-time safe, we need to avoid these. So what do we do about this? Well, first of all, we need to understand the problem. So I tried to really figure out what the use case was and why this problem was arising. And it essentially boils down to plugins using the Juice audio processor value tree state and hosts calling set value of parameters from the audio thread. And they do this because if you have a host that has automation curves or someone's moving a slider or something like that, they can queue up parameter changes, they process them all, and then they call your process block. So they're effectively setting your parameters to what they want it to be before they process. Does that make sense to everyone? Okay. But when you do this, this is going to call a callback, which is parameter value change. So anything that's listening to this audio processor value tree state, or audio processor parameter rather, is going to get notified that that change happened, which is kind of what you want. It's a callback. And the real problem comes in when attached control base registers itself as a listener, gets this changed callback, and then ends up calling trigger async update. And this is what Rusty Pine on the forum highlighted. So we're in this case here. If it's not the message thread, then we need to trigger async update. So this kind of makes it thread safe. And the use case here is that if you're writing a plugin UI, you'll have a bunch of sliders, buttons, etc. If automation comes in, changes those values, you need to then update the slider values based on what the actual value is. So that's how this happens. So that's the problem. What can we do about it? Well, we know that we can't use anything that calls post message. We've already established that's not real-time safe. And what that essentially means is we can't use Juice Async Updater from a real-time thread because that internally calls post message on Windows. So I thought, well, let's propose some solutions. Let's not just kind of bike shed it on the forum for ages. Let's figure out what it takes to kind of solve this problem. And I'm calling this part create a real-time async updater. Okay, so we're trying to get a real-time guarantee from it. Lots of code. Don't worry about it. The left-hand side is the Juice Async Updater. The right-hand side is the version that we're going to build. And they look almost identical because they are. I just copied the class because I wanted an exact same interface so it would be a drop-in replacement, and then figure out what it takes to build that, basically. The only other difference is the members are slightly different, which we'll see here. The internals of Juice Async Updater are kind of like a pimple. You have this message that is internally reference counted, and it essentially holds the state to whether it should be delivered or not. And in the version we're building here, we've got effectively the same thing, just with a different type. Write some tests. That's good advice. So when we're trying to make something better, we need to have a baseline, and we need to figure out how the changes we're making to it affect it. So this was my test. It's the Juice unit test framework, but essentially you just have one method called run test, and then you can just call this function called expect to make sure things are true. And I decided to template this. So we've got two tests. We've got the run async update test with the Juice async updater, and then the run async update test with the version we're creating. And the reason I did this was because it means the interface has to be the same because it's a template. If we start adding methods or changing, removing stuff, then this is going to fail to compile. The other thing it means is that the tests that are run on it are going to be exactly the same because it's effectively the same code. So we have this templated function which is going to run the tests, and then we have this templated struct or class that is going to actually be the body of our test. So this is the kind of body of our test. We effectively have two things, send update and handle async update, and we're going to measure the time between them. And to do this, we need a waitable event, which is how we're going to pause our thread to wait until that update has been handled, and we need an atomic to let us know whether that has actually been delivered or not. So that's going to be our test, basically. So in our send update, that's what's going to be called from the real-time thread. It's going to be calling send update. We say, has it been delivered? Reset that to false. trigger our async update, which is going to post some message somewhere, and then at some point in the future, our handle async update is going to get called. We set our flag to true and signal whatever's calling us on this event to continue. And we're adding this assertion here because this has to be on the message thread. If it's not, then it kind of defeats the whole point of doing it. Does that make sense so far to everyone? Okay. So in our function that's going to actually run the test very quickly, because it's not that important, we create our updater test, we create a performance counter, which essentially we can start on top, stop, and then we get some statistics from that. And we need this atomic flag to tell us when we've finished. Because this is multi-threaded stuff, and normally your callback would be happening on the process call, we're going to kind of replicate that with a thread here. Otherwise, we're just posting on the message thread, and that doesn't really make any sense. So in our tight loop of our test, we're going to do it 10,000 times, and then we're going to start a performance counter, send our update, wait on that event for it to be signaled, and then when the update has been delivered, we can continue and stop our performance counter. So what we're measuring here, and this is important, it's different from before. We're not measuring the cost of calling trigger async update anymore. We're measuring the latency between sending an update and it being and the callback happening. Does that make sense to everyone? Okay, because all the graphs from this point onwards basically going to be showing that. Okay, we have a test just to check whether it has indeed been delivered. Otherwise, obviously, the test has failed. We've broken something. And then while we haven't finished this test, we just have to pump the message loop to make sure these messages get delivered. Okay. So this is a kind of quick conceptual idea of what trigger async update does. If we think about time moving forwards in our application, we can call trigger async update, and then we have two important characteristics we need to measure. The first is the trigger async update cost, which is how long it takes to call this function. And then the second, when we receive our callback, is the time between them. I kind of just mentioned that, but that helps to kind of cement it. So it's that round trip latency we're looking at here. With the Juice async updater, we can see roughly an average of 20 microseconds, a minimum of 5 microseconds, and a maximum of around 100 microseconds. And if we stick that on a graph, we can see it looks like this. See this gap here? That's our minimum and our average and our maximum at the top. So that's our baseline. That's the performance characteristics that are currently being used in the attached control base. And we're going to figure out what deviations from that happen. So we need to implement this real-time async updater now. As I said, most of the internals are almost identical, but instead of doing this atomic setting and posting, we're going to combine all of that into a single post update call because the logic gets a bit different. So our internals of our message look like this. We are real-time async updater message now. We need to know about our owner because we need to call its handle async update callback. We need this atomic because we're going to be firing it from different threads, whether that callback should be delivered. And this is the main difference here. Before we were using post message to kind of use the system queue to call things back, but now we need to handle this ourselves. So we've got this shared reference to what we're calling a dispatcher, and that's going to be responsible for actually calling our callbacks. So we need to register and remove ourselves from the dispatcher. Then we have this post update that all it's going to do now is call set on our atomic. So this is the key difference. This means this is now real-time safe. Remember before, this was calling set for the atomic and then post message, and that was causing all the problems. Now we've removed that. So we know this is real-time safe. At some point in the future, our dispatcher is going to come round and call service message, and it's going to check the value of this should deliver flag, and if it was set, we'll reset it and call our callback. Okay? Any questions on that? One at the back?
Not at that one, but the step before. Why
So the question is, why are we measuring round trip latency? And the answer is because that's the thing that changes. As we do different approaches to things, we're going to change the performance characteristics. And you say, yeah, we're doing UI updates. For this example, we are, but we're changing a library function to make something else. So the point is, we need to consider how things are changing. And that's what I'll dig into a bit, okay? So, trade-offs. We now have a real-time safe way of posting a message. But how do we service these messages? We need to kind of call the callbacks some way. We can't use system calls, as I mentioned. We need to manage this ourselves, so we need to implement the dispatcher. And that means we have to decide what's acceptable. Yes, you might be able to do it in a kind of 25 frames per second way, but that might not be good enough for some other async updaters. I know we have use cases where we use juice async updater, and doing it on that kind of frequency just wouldn't be responsive enough. So we have to decide things about this round trip latency. We have to think about CPU overhead. Does that change? And the ordering of callbacks, which may or may not be important, and I'll come back to that later. So here's the first stab at implementing our dispatcher. We're going to have an array of updaters. So these are the messages that get registered with us, and we need to be able to add and remove them. And then we're going to implement from timer and then start a timer at 25 hertz. This basically is what you were saying a minute ago. So we've already chosen here a characteristic about how this dispatch is going to behave. We're saying it's running at 25 hertz, which is roughly 40 millisecond intervals. That might be okay, might not be okay. Maybe you want to run at 60 frames per second. You're already making hard decisions at this point. And then when the timer callback happens, we're going to call service updaters. So at some point, when this timer calls back, we're going to iterate through all of our updaters and call them. So here's the add and remove. They're not very interesting. And then service updaters, we're just going to take this lock so we make sure we're not modifying the array as we iterate it. And then we're going to call service message for all of our updaters. As you can see here, this is one of the first problems we have, in that because we're iterating this updaters array, we're always going to call the callbacks in the order that they get registered, which is a different characteristic from the juice async updater. And that may or may not matter. If you've got a bunch of sliders on the screen and you just want them to, at some point in the future, reflect the true value, probably doesn't matter. But certainly when you're doing things like using async updaters with value trees, it almost certainly does matter. So our service message simply checks the value of our atomic, as I mentioned before, and calls the callback if necessary. So this was our juice baseline, remember? This is our timer-based real-time async updater, and here's the difference. Our average before was 20 microseconds. Our average now is 40 milliseconds. Minimum was 5 microseconds. Now it's around 200. And the maximum before was around 100 microseconds. Now it's 92 milliseconds. So we've completely destroyed the latency that we had before. And if we stick that on a graph, we can't even see the juice version anymore. It's massively different. So you can see how we've changed the behavior here. And that makes sense. We've started a timer here, and we've started it at 25 hertz, which is around 40 milliseconds. So we can think in terms of time running through our application. In our test case, we've basically started by calling post update, waiting for the timer to call back, and then call service message, and then almost immediately posted another update, and then waited for service message to get called on the timer callback, and so on. So you can see we would expect this to average out at 40 milliseconds, and the timers aren't spot on, which is why you kind of get that huge variation. But this isn't really how a real-world use of this would look like. You'd probably end up with a lot of trigger async update calls. So what you'll probably get is an average of around 20 milliseconds with a jitter of around 40. So what we've done is we've engineered a solution which has an average latency, in this test case, of 40 milliseconds and a jitter of around 80 milliseconds, which isn't anything like what we had before. We've got an additional overhead that a timer's now running, and that's going to be continuously running. And if you have an application with lots of timers, perhaps that timer running is going to introduce a cost there. But it is real-time safe, and that was the whole point of this. So you can hammer it from any background thread with effectively no cost. And as I mentioned, the callbacks will happen in the order that the real-time async updaters are created, and that may or may not be problematic. So can we do better than this? Well, there's another approach, which is to implement our dispatcher, which is to use a thread, essentially. I'm going to hide all the bits that haven't changed. So in this example, we're inheriting from high-resolution timer, which internally runs a thread that has a waitable, or it just blocks a thread for a specific period of time and then has a callback. So we still have start timer, but this is in milliseconds now. And I thought, well, we're running a background thread, so we're kind of moving the overhead from the message thread, which could grind your application down, and we'll make this 5 milliseconds. We have our high-res timer callback, but this happens on a background thread now, so we need to use the juice async updater to call trigger async update, which at some point in the future is going to come around and call handle async update, and then we can service our updaters. So one of the performance characteristics you might notice about this is its best case is going to be as bad as the worst case from before, because you're still using the trigger async update to get things onto the message thread. But it's real-time safe. And also, there was some overhead because we were always calling trigger async update every time a callback, but actually we only want to do that if anything has actually triggered the callback, so we can introduce this new atomic to see whether it needs to service any updaters and set that in this signal method. And that changes what our post-update method looks like a bit. We have to set the flag, but now we have to call this signal method. And then when we call back, we just check this, reset it, and if it was true, call trigger async update. Okay, so what does that look like in terms of performance characteristics? Well, now we have this very steady average of around 5 milliseconds, minimum just below it, maximum just above it. So we've got a very rock steady timer interval now. It doesn't quite have the jitter that we had before. So we've got much more stable latency, and because we're using the background thread and I chose that 5 millisecond number, it's a lot lower than it was before. And that's what it looks like on the graph. So you can see much lower but much more stable as well. But we're still not seeing it to be relatively comparable to what Juice was before. So if we summarize, we've engineered a solution which will have an average latency of around 2.5 milliseconds with the jitter of around 5 milliseconds. It requires an additional thread to be running. Again, we're talking about a library class here. So do we want to be spinning up threads to service these dispatchers? You need to think about that. It's relatively low CPU overhead though, apart from the thread running. And it is still real-time safe because we're only setting that atomic from the message thread. So to recap, we've created two solutions which are real-time safe. They return instantly from trigger async update, which is good. But both have additional overheads. We've kind of moved them around from the costs of calling the callbacks, introducing threads, etc. But they both have worse average latency than Juice Async Updater, and that is going to be important when you use it in your application. So, but it seems like what we're doing is essentially engineering a really complicated solution to just getting a slider to change its value when an internal value changes. So perhaps this isn't the right approach. Maybe we should be thinking about something completely different. But then I thought, well, is there a way to get closer to the characteristics of Juice Async Updater with making some other trade-offs? And in this instance, we're implementing our dispatcher, but instead of inheriting from a high-resolution timer, we'll inherit directly from thread. This gives us more control over its characteristics. So we're going to start our thread, and this just uses the default priority, which I think is 5, but could this be lower? Does it need to be higher? Again, that's something that you need to think about. And while our thread's running, we're just going to make sure that we're not destructing. That just avoids a potential hang-on load. And we're going to wait on this waitable event. And then essentially what's going to happen is when messages need to be posted, they're going to signal this event. Then we can continue from this point in the thread, call trigger async update, and then at some point in the future, we're going to service our updaters. So we can see that this waitable event here is going to be wait and then signaled. Does that make sense to everyone? It kind of works like a latch. Okay, and in the same way before, when we call post update, we need to set our flag and then signal the dispatcher, which is going to signal this service event. Let's have a look at the performance characteristics. We can see that we have an average now of 20 microseconds, minimum of 7 microseconds, and a maximum of around 7 milliseconds. Okay, so that's our round trip latency again. And if we stick that on the graph, we can see how that's very different from the two previous solutions. We're now, on average, about comparable to Juice. And if I get rid of the timer, because it's kind of skewing the graph, you can see how, on average, it's very comparable. It has a slightly worse case scenario, but that could be introduced by the Juice async updater, or perhaps a long time for the thread to wake up. But waitable event, can we use that in a real-time context? So let's summarize that solution. We've made a low latency version. It's comparable in terms of performance to the Juice async updater. It's low CPU overhead. It's essentially just got an additional notify all cost. But that means it's not thread safe because we've used this system call. We're interacting with a thread scheduler. And as we know, we can't do that if we want to have real-time guarantees. And also, we still have this problem that it requires an additional thread to be running. So the signal call on the waitable event ends up going through a stood condition variable notify all, as I said, which is a system call. And because that interacts with the thread scheduler, it could block. And that means it's not real-time safe. So perhaps this isn't, or we shouldn't call this a real-time async updater. Perhaps this should be named something like low latency async updater, okay? Because that better describes its performance characteristics. But if we actually go back to our original case where we were measuring how long it takes to call the trigger async update call, we can kind of compare these things. So the Juice one had this high worst case. Remember, this is the call of triggering the async update now. And you can see this was the problematic bit at the top here. The two solutions that use the atomic in the middle are very good. And the waitable event is actually comparable to this. So you might think, well, actually, can we use this? This gives us all the benefits of the low latency version, but is kind of nearly perhaps real-time safe. Would you use it in a self-driving car or a plane? Probably not. Would you use it on a general purpose laptop running plugins? That's for you to decide, really. I think what this shows us is we need to measure real world cases more and figure out what the different performance characteristics are, and also be aware of your use cases. So that's kind of it. I said there wasn't going to be a real final solution. It's going to be a series of questions. And here's essentially the things that we've kind of traded off as we've kind of gone along. Real-time versus non-real-time guarantees. Library-created background thread versus timers that are running. Minimum latency versus jitter versus additional CPU overheads. And maybe what we've actually done is created a solution that isn't really suitable for a general-purpose library. Maybe the attached control base should just run its own timer and just check for values internally. That would be real-time safe, and it wouldn't kind of impose all these predetermined characteristics on us. But the message here really is to think about your use cases and trade-offs. For a lot of people, as Daniel said, we're just running a timer to refresh the screen. That's fine. But if we're trying to make something real-time safe and put it in a library, we need to think about what are all the ways people are going to use it and how to describe the performance characteristics. And I mentioned there was a few problems. We had the order in a callbacks problem, which again may or may not be problematic. Roland Rabin, who works with me at Traction, instantly we ended up, for fun, looking at this problem on the same day and coming up with almost the same solution with the condition variable. And he solved the ordering problem by having a counter that just gets atomically incremented, and then each of the update messages take a number, and then when you dispatch them, you can sort them in the order that they got called in. There's another approach as well that you could use a lock-free queue, so you kind of push them into a queue, and then your dispatcher empties the queue. So there's lots of different things here, although I didn't want to dig into them too deeply today. We could think about a template parameter for the timer interval. That would mean that a user of your library could then use a template parameter to have a really fast timer if that's what they needed. But then you need to think about if it's going to be running a thread internally, then every different number for the timer interval is going to spin up a new thread. So you're kind of messing with stuff there. Just things to think about, really. So that's it, I'm afraid, or you'll be glad. Well, are there any questions on that? One question here.
So I have a question. So you said condition variable notify all is a system call. Well, obviously, at least it has to like lock a mutex. So maybe it's too generic of a question, but like, let's say we are producing audio, right? We're like on the audio callback. We're actually pumping stuff out over the speakers. When is that fine to do that? Like, do you have any kind of advice on that?
Define fine. Do you get away with it?
Like, none of my users will ever say your product doesn't work because it glitches.
Well, they might, and that's what I would say why we can't accept that as a solution to this. But if all of your production code ever uses this and it's never a problem, then was it really a problem to start with? It's about your guarantees, really, and can you measure it? I would say lots of people probably are doing stuff like this, but they might also have plugins or audio code that occasionally drops out and people never notice. Maybe they correct it in post. I would say advise against it. Use a real-time safe solution if you want to be real-time safe. But as a characteristic that's similar to the Juice async updater, but doesn't have that 47 millisecond occasional overhead, it's probably the most similar but performing slightly better. So maybe you want to do that first and then think about your system in terms of making it real-time safe. Because the other thing here is what I hope this summarizes is making something real-time safe isn't like clicking your fingers or flicking a switch and just suddenly it's all real-time safe. It really means that you have to think about how your problem works differently. And going through this process helps you think about this and go, well, yeah, this probably isn't acceptable. I don't like this timer. This isn't quick enough in this solution. So you kind of really need to engineer your system slightly differently. Any other questions? Okay, thanks very much then. I'll hand back to Timo.
This fantastic talk. Thank you once again for coming, Dave.
Do you want to just hook into this thing?
Yes. Okay, great. I'm going to do a very quick talk for the beginners. Once again, how many people are using Juice at the moment? Just raise your hand. So there are quite a few people that here that haven't used Juice or maybe are unfamiliar with Juice and would like to get into it. So what I'm going to do as best I can, because my laptop's down here, I have one hand committed to the mic, is I'm going to give you a very quick introduction to Juice, just in case you haven't checked it out yet. Haha. You can hear me. You can hear my own voice. Isn't that funny? So that's my live stream. How come we mute that? Yeah. So I'm just going to do this really quick introduction to Juice. So if you don't have Juice and you're looking to get it, you can go to shop.juice.com/get-juice. You can download it there. You have a couple different license options here. if you're in school or if you're like me using a personal license, you can just download it. It's free. And then you just have this splash screen that appears in the bottom right-hand corner. It says Made with Juice. If you're indie, you can pay $35 a month. That's if you earn less than $200K a year. Or if you're earning the big bucks, then you can go with the Pro plan, which is $65 a month. So when you download Juice, I'm just going to go through what you actually get. When you first open up Juice, this is what you'll see. You have a couple different templates that you can go with here. So you have an audio application if you want to make a DAW or a standalone application. You also have a audio plugin. And what these do is if you click on these, you can actually, they'll set up your kind of template files to get you ready to actually build these type of applications. Another thing that's really useful is if you go down here to the bottom right, Juice actually has a bunch of useful tutorials courtesy of the Juice team, where once you click on that link, you actually have a whole bunch of tutorials on audio, on building a synth, MIDI, plugins, DSP, graphics, interface design, mobile, and all kinds of utility classes. And if that wasn't enough, you can also browse Juice demos. So if you click this center button here, this will actually open a app called the Demo Runner, where you can actually browse different demos. So these actually have most of the different pieces of example code. So all you do is you just click in here, click on one of these, and then you have just this code here. You can actually look at the code itself as well. So you can check out the code there like that. You have your settings here if you want to change your sound card. So that's the Demo Runner, which is kind of a all-in-one solution if you want to check out all of the demos. But you can also just check out one of the demos, one of the pieces of example code at a time. If you go to Applications, if you're on a Mac, you go into your Juice folder, and you can go into Examples, and then you can pick one of these. So like, let's just do UI, and then what you have are these little files here, and all you need to do is just click one and drag it into your producer if it lets me do it. There we go. And see, it formulates a project here for you. Then all you do is just click on the center button here, and then this allows you to save the project. So you just have to save it. So I'm going to save it here to my desktop. You see here it's just saved a new project to the desktop, and now it will open it up in Xcode, and then I can just build it. And it's just building. And while it's doing that, I will show you one more thing. So one other thing I'll point out for beginners is if you go into the project itself, if you go into the project itself, you'll actually, this is kind of the structure of a Juice project, which is that you have all of your builds. If you're running on different OSs, all of your build files will be in here. You have your Juice library code, which is all contained here. So these are your core kind of framework files. Then you have your own source files here, which are contained here, and your Juicer project. One key thing to keep in mind, so this is actually the built file, so these are some widgets here that you can use. So very useful if you're trying to figure something out. Normally there's a good example in the Juice examples that you can check out. And one other thing just to keep in mind is that when you're trying to add new source files, make sure that you add them from the Juicer rather than just adding them in Xcode, because what will happen is if you add them in your IDE, they'll actually disappear. So make sure that you add them in the Juicer and use save and open in IDE. So that's it. That's an introduction to Juice. Hope you enjoyed it, and thank you very much. Let's have a beer. Thank you. Thank you to, I want to give a quick shout out once again to our sponsors, Focusrite and Sonox, for sponsoring us And we have some food that we're going to actually be serving very shortly. So we have some finger food. And also make sure you grab some drinks at the bar. Thanks once again to Strong Room for supporting us and having us here. And let's have a great time.